So, we have just discussed that sag of the conductor decreases because its tension pulls the conductor up, right. But at the same time tension elongates the conductor from elastic stretching, which tends to relieve tension and sag increases, right. So, that means that the elastic property of wire is measured by its modulus of elasticity. This you know actually. The modulus of elasticity is defined as the stress per unit area divided by the deformation per unit length. That means, sigma is equal to T upon A kg per meter square. This is equation 1, where sigma is equal to stress per unit area, that is kg per meter square, T is equal to conductor tension in kg, and A is equal to actual cross section of conductor, that is in meter square. So, elongation E of the conductor due to the tension is that elongation E can be defined as that E is equal to stress divided by modulus of elasticity. This is equation 2. So, elongation is high, E is high, that is elongation, if modulus of elasticity is low, right. Thus, a small change in the length of conductor causes large effect on sag and tension of conductor. Now, if you see that sag and stresses in conductors are dependent on the following points. One is initial tension put on them when they are clamped in place, right. 2, weight of the conductor themselves, ice or slit clinging to them, and then wind pressure, right. So, these are the things that sag and stresses actually dependent of these following things. So, particularly ice or slit clinging to them, it is basically in the mountain area where snowfall is there. Therefore, that stress actually depends sag, any span can be used provided the poles or towers are high enough and strong enough. But if you make poles or towers are high, and then naturally that your height of the tower will increase, therefore, cost will increase. The matter is merely are of extending the catenary in both directions. So, cost of tower sharply increases with height and loading, right. Now, another thing is the effect of temperature change. Common sense says that in summer that sag will be more, and winter it will be less because of the temperature variation. So, sag and stress vary with temperature because of the thermal expansion and contraction of the conductor. Temperature rise of conductor increase the length of conductor, and hence sag increases and tension decreases, and vice versa. And similarly, the temperature fall, that is in winter, say causes just opposite effect, right. So, maximum stress occurs at the lowest temperature when the line has contracted and is also possibly covered with ice and slit, right. So, this can happen particularly in the winter. So, if conductor trace is constant while the temperature changes, the change in the length of the conductor can be given as delta L is equal to L 0 into alpha into delta T. This is equation 3, where delta T is equal to T 1 minus T 0 and delta L is equal to L 1 minus L 0, where T 0 is initial temperature, L 0 is conductor length and initial temperature say T 0, that is this is T 0, L 1 is conductor length at temperature T 1, and alpha coefficient of linear expansion of conductor per degree centigrade, and delta T, that is this one delta T and delta L, this delta T is change in temperature in degree centigrade, and delta L change in conductor length in meter, right. That means that if the temperature is constant while the conductor stress changes, that is loading, the change in length of the conductor is, it can be given as delta L is equal to L 0 into delta T divided by m into A, where delta T is equal to capital T 1 minus capital T 0, where T 0 is equal to initial tension of conductor, that is kg, delta T is equal to change in conductor tension, that is in kg, m is equal to modulus of elasticity of conductor, that is kg meter, and A actual metal cross section of the conductor, that is in meter square. Now, these are some simple thing. Now, calculation of line sag and tension. Actually, we have taken a catenary shape. These are symmetrical, although my handwriting is slightly this way, but this side and this side it is symmetrical, right. So, this is your, suppose it is your both the side, this is tower side, this one and this one, they are of equal height, right. So, this is the first thing. So, figure 1 shows a conductor suspended freely from two support. This is one support, this is another support, the tower side, right, which at the same level, that is same height, same level, and I mean if from this is a horizontal distance, right, and if sag and tension, if sag happens in conductor, so basically it takes a catenary shape, right. So, they are at the same level, that is, and the horizontal distance between them is capital L, this is capital L. Takes the form of catenary curve, providing the conductor is perfectly flexible and conductor weight is uniformly distributed along its line. Actually, total length of the conductor is small l. So, from here to here we have, this is L by 2, this side also total is L by 2, right, but we have taken some point your P. So, in this case, that when sag your d is very small, when d is very small in comparison to span L, that is that conductor is tightly stretched, the resultant curve can be considered as a parabola, right. But in this case, the parabolas we will see later, but in this case we have not assumed that this is a parabola, it is a catenary shape, but if sag is less as compared to the L, then that can be considered as a parabola. So, this regarding this your point P, then V is equal to W s, then horizontal your tension H, then tension T at point P, T x, T y will come little bit later. So, if your d less than 0.06 L, suppose if it is total your distance between the two towers is L, horizontal distance, and d is your less than 0.06 L, the error in sag, right, computed by the parabolic equation is less than 0.5%. That means, if your if d is less than your what you call that 0.06 L, L is the your distance between the your two support or two tower, horizontal distance, then error is very small, just 0.5%. If d is lying in between 0.06 L and 0.1 L, then the error in sag computed by the parabolic equation will be about 2%, that is also quite less anyway. So, now catenary methods, that is supports at the same level. So, this is that both the supports are at the same level. Now, figure 1, this is your figure 1, this is figure 1. It shows a span of conductor is two supports at the same level and supported by a horizontal distance L. This is the horizontal distance L, right. Now, this O, this is the O is the point, is the lowest point on the catenary curve, right. This is the lowest point at the catenary curve, and this D is the maximum sag, D is the maximum sag, right. And L is the length of the conductor between these two, but it has taken a your catenary shape. So, this is the midpoint. So, this length is L by 2, from here to here it is L by 2, right. So, this is that half, this L is the length of the conductor, and if W is the weight of the conductor per unit length, this W actually is the weight of the, this is cap W, this is W, right. So, W is the your what you call weight of the conductor per unit length, and if your T is the tension of the conductor that is at a point T, right. This is the T is the tension at point P, and your in direction of curve, and H is the tension kg at origin, and H this is the horizontal tension. So, this T is acting in the direction of the curve, and its horizontal component is T x and vertical component is T y, and this angle is your between T and T x is theta, and distance from this horizontal line from this minimum, that is O is that your lowest point of the conductor, there is maximum, and here the sag is maximum, this distance is y, small y, and from O to this point P, that is OP, this distance is x, O to P, that distance is x, that means here to here, and from point O to P, we assume the conductor length is a small s, this is small s, and if the W is the weight per kg meter. So, total vertical force will be acting on it, V is equal to W into S, where W is equal to kg per meter and S in meter. So, this is at some point P we have taken, and the weight is uniformly distributed. Therefore, this point you can this point, the middle point between O and P, this is the middle point between O and P, that V is equal to the vertical weight W S say is acting downwards, right, assuming that weight is, and conductors are your round shape, and this assumption is correct, right. So, in that case tension T, this tension T, it can be resolved T in two component, one is horizontal component T x, another is vertical component T y. So, if you see that your force or tension balance equation, then T x will be equal to H, that horizontal tension, and this T y is equal to V is equal to W s, right. So, if we, that means this, if we make a triangle here in this figure, this figure, that this is a horizontal tension H, and this is your T y, that your this V is acting downwards, right. So, this is V, T y is equal to V, and T x is equal to H. If you make this triangle, and this is tension T, and this angle is theta, that means tan theta will be as actually is equal to V upon H. Therefore, just hold on. So, that means T x is equal to H, this is equation 5 I told you, and T y is equal to W into S, this is equation 6. Thus, the portion OP of the conductor is in equilibrium under the tension T, that is this portion OP is in equilibrium under the tension your T, right. At point P, the weight W s acting vertically downward at the horizontal tension H. So, this I told you that W s, this is the midpoint between O and P, and it is you are acting vertically, and this is the horizontal tension, this is H. Now, suppose if there is a your certain your little bit of increase in the conductor length, your say this is the conductor length, if there is a little bit of change in the distance, say it is S, suppose there is a little change in ds, then naturally your this is you have taken in catenary shape. If we make a triangle, then horizontal side will be dx and your vertical side will be dy. So, that is why now this is your figure 2. So, in figure 2, it is a triangle where ds represent a very short portion of the conductor. You take a very short portion of the conductor in the region of point P. Now, this is your point P. I mean, in the vicinity of this one, if you consider that your what you call small distance ds. So, if when s is increased by ds, that is why I tell you that the small increment is corresponding to x and y are increased by dx and dy respectively. That means, just hold on, that means if you little bit of increase say ds, naturally this distance is y from here to here, and this O to P, that is horizontal one, it is P for your this thing. Suppose I can make this one also P dash. So, OP dash actually is equal to x and P dash P is equal to y, so, right. So, if there is take a small distance ds, so naturally corresponding horizontal one distance one will be dx and vertical one will be dy. That means your if this is ds along the conductor, the horizontal one is dx and vertical one is dy, and this angle is theta. That means, tan theta is equal to dy by dx. Therefore, we can write tan theta is equal to dy by dx is equal to V by H. That means, this theta and this theta same. So, tan theta here is equal to V upon H, and from here tan theta is equal to di upon dx. So, tan theta is equal to di upon dx is equal to V upon H, and V is equal to W into S. Therefore, we are substituting V is equal to W into S. So, basically tan theta will be W S by H, that is dy by dx is equal to W S by H, right, and this is equation 7. Now, from figure 2, from this figure, this is a right angle triangle. So, d square is equal to dx square plus dy square. That means, from figure 2, that means from this figure, d square is equal to dx square plus dy square. That means, just divide both sides by dx. So, ds by dx whole square is equal to 1 plus dy dx whole square. This is equation 8, right. But just hold on, but we have seen that your dy by dx is equal to actually ws by your h, right. So, that means, this dy dx is equal to ws by h, you substitute here ws by h. If you do so, then ds by dx whole square is equal to your 1 plus ws by h whole square, right, or dx is equal to ds upon root over 1 plus ws by h whole square. This is equation 9. Now, if you integrate both sides, then x will be integration of ds upon root over 1 plus ws by h whole square. If you integrate this, it will be x is equal to h by w. This integration, I think you can do it, I need not do it, right, you please do it, right, it is a simple thing. So, h upon w sin hyperbolic inverse ws upon h plus k is a constant. So, this is equation 10. Now, if I put the boundary condition to get the value of this k value. So, here when x is equal, if you look at this figure, when this is x actually O to p dash x, if x is equal to 0, then naturally s also will become 0, because s is measured from this point. So, if x is equal to 0, then s is equal to 0. If it is so, then you put the condition that x is equal to 0, then s is equal to 0. Then you will find that k is equal to 0. So, in this case your k will become 0. So, therefore, x is equal to h upon w sin h inverse, that is sin hyperbolic inverse ws by h, or s is equal to, we can write h by w sin hyperbolic wx by h. I mean cross multiply wx by h, and then you just you simplify. So, we are writing s is equal to, this s is equal to h by w sin hyperbolic wx by h. This is equation 11, right. Now, when x is equal to L by 2, s is equal to L by 2, that means this figure. So, x is the horizontal distance. So, from here to here it is L by 2, because from this support to this support is capital L. So, it is a midpoint. So, when x is equal to L by 2, then this side also half of the conductor length. So, small s is equal to small l by 2. Therefore, when x is equal to capital L by 2, s is equal to small l by 2. So, if you substitute here, in this equation, you will get s is equal to L by 2 is equal to h by w, then sin hyperbolic, then w l upon 2 h, or L is equal to 2 h by w sin hyperbolic w l by 2 h. This is equation 12. Now, what you can do is, you expand this sin hyperbolic w l by 2 h in series. If you expand it, it will become L is equal to 2 h by w 1 upon 1 factorial w l upon 2 h plus 1 upon 3 factorial w l upon 2 h whole cube plus the higher order terms. So, and if you take only this first two term, this term and this term, you take w common and h common, they will be cancelled. Finally, this expression L will become that is equal to capital L into 1 plus w square L square upon 24 h square. This is equation 13, right. Just you take from this equation w common and your h common and simplify, and as well as L common, you take h common, w common and L common, you take h and w will be cancelled. You will find small l is equal to capital L into 1 plus w square L square upon 24 h square. This is equation 13. Now, from equation 7 and 11 we get. Now, equation 7 we have seen, not showing it again, understandable. We have seen that dy by dx is equal to ws by h. This is at equation 7, right, and your s is equal to the w sin hyperbolic w is equal to sin hyperbolic wx by h. Just let me find out equation 11, I will show you. that this is, just hold on, so this is equation 11, this is equation 11, right. Here it is S is equal to h by w sin hyperbolic w x by h. In your equation it is your this w s by dy by dx is equal to w s by h. So, if you cross multiply, it will be w s by h is equal to sin hyperbolic w x by h. That is why you are writing dy by dx is equal to w s by h. This is known, w s by h actually coming from this equation 11 multiplied, this cross multiplication w s by h is equal to sin hyperbolic w x by h, right. So, therefore, dy is equal to your sin hyperbolic w x by h into dx, this is equation 14. So, integrating, you integrate this equation both side, integrating both sides of equation 14, that y is equal to integration of sin hyperbolic w x upon h into dx, right. So, that integration sin hyperbolic, sin function integration is cos hyperbolic, right. So, it will be actually y is equal to h upon w cos hyperbolic w x upon h plus k 1. This is equation 15, where k 1 is the constant. Now, if the lowest point of the curve is taken as the origin, that is when x is equal to 0, y is equal to 0, because this is the point is origin. So, at this point x is measured from this point only. So, when x is equal to 0, then y is also is equal to 0, because this is y, this is x, this is y. In general, coordinate of this point is x y. So, when x is equal to 0, y is equal to 0. That means, if you do so, cos hyperbolic 0 actually is equal to 1. Therefore, small y is equal to h upon w, then cos hyperbolic w x upon h minus 1, this is equation 16, because you will get, if you put x is equal to 0 and y is equal to 0 in this equation, you will get k 1 is equal to minus h by w, right. And after that you substitute here k 1 is equal to minus h by w, take h by w common. So, you will get y is equal to h by w cos hyperbolic w x by h minus 1, this is equation 16. Now, the curve of equation 16, this one is called a catenary, right, and equation 16 can also be written as y is equal to, small y is equal to h by w, this cos hyperbolic you expand in series, and consider only first two terms. So, it is 1 plus 1 upon 2 factorial w x by h whole square, then the higher order term neglected, bracket close, minus 1, because this minus 1 is here. So, this minus 1 will be cancelled. If it is so, then it will become actually that your w, because if you take this is w square h square and h by w. So, 1 h and 1 w will be cancelled, and ultimately it will become w y is equal to w x square upon 2 h, this is equation 17, right. And from figure 1, I mean from this figure that is t, this is right angle triangle. So, t square is equal to h square plus v square, here it is t square is equal to h square plus v square. That means, t is equal to root over h square plus v square. If you take h common from this equation, so t is equal to h in under root 1 plus v upon h whole square, right. This is equation 18, and equation 7 we have seen v upon h actually is equal to dy upon dx. So, here this is equation 7, it is given that it is dy upon dx is equal to v upon h. So, we are putting t is equal to h root over 1 plus dy upon dx whole square, this is equation 19. So, from equation 16 we get that dy upon dx is equal to sin hyperbolic w x upon h. That means, this is your equation 16, this is your equation 16. You take the derivative with respect to x, it will be dy upon dx is equal to h by w, and it will come out w into w by h, then sin hyperbolic h. So, h cancelled, w will be cancelled, and it will be sin hyperbolic w x by h, not showing here, because this is a simple thing and understandable to you, right. So, that means, we get that dy by dx actually is equal to sin hyperbolic w x by h, because this one actually it will come this one your what we call this one your y is equal to your h by w cos hyperbolic w x by h, right. So, if you that means, your ultimately dy by dx will come, that is sin hyperbolic w x by h. So, in this case your what you call that this is from equation 16, that is from equation 16 we are getting dy by dx is equal to your sin hyperbolic w x. Just take the derivative of this equation, simply this equation, right. Then what you do, this dy by dx, that is see your equation 19 and 20. So, dy by dx if you put here in this equation, it will be root over 1 plus sin hyperbolic square w x by h, right. So, 1 plus sin hyperbolic your w x square, it will be cosine your what you call that cosine hyperbolic w x by h. Actually, it is very simple thing, right. So, your for example, your y is equal to h by w, then this is cos hyperbolic, right. Your w x divided by h minus 1. So, if you take the derivative of this one, then dy by dx will be h upon w into w upon h, then sin hyperbolic your w x by h, right. This one will be cancelled, is equal to sin hyperbolic w x by h. Now, if you put in that equation that and now root over, it is given t is equal to h root over 1 plus dy by dx whole square, that is equal to h, then root over 1 plus sin hyperbolic square w x by h. Actually, this is nothing but cos square cos hyperbolic square. So, it is cos hyperbolic. So, it equal to h cos hyperbolic w x by h, right. So, this is the thing, that is why this equation 21 from equation 19 and 20, sorry, I am writing t is equal to h, then cos hyperbolic your w x by h. This is equation 21. So, where the total tension your in the conductor, the support x is equal to L by 2, that is if you look at the figure, that is this is total distance is L and this will be L by 2. So, when x is equal to L by 2, sorry, then the total tension in the conductor of the support at x is equal to L by 2 is, that means t is equal to h cos hyperbolic. When x is equal to L by 2, you substitute in equation 21 x is equal to L by 2, here it will be W L upon 2 h. So, h cos hyperbolic W L upon 2 h, this is equation 22. Now, if you expand this cos hyperbolic W L by 2 h in series, it will be t is equal to h, then 1 plus 1 upon 2 factorial, then W L upon 2 h whole square plus 1 upon 4 factorial W L upon 2 h to the power 4 plus higher order terms and so on. This is equation 23. Now, the sag or deflection of the conductor for a span length L between supports on the same level, that is at x is equal to L by 2 and your y is equal to d. So, from equation 16 that means this equation, actually so many equations are here. So, from equation 16, right, from this equation only, right. So, and this is your what you call that diagram, that figure 1. So, the sag or deflection of the conductor for a span of length L between supports on the same level, that is at x is equal to L by 2, y is equal to d. That means, this is your what you call the total is your L and half is L by 2. So, at x is equal to your what you call L by 2, y is equal to d, and then equation in equation 16 you if you put this one, that when x is equal to L by 2, y is equal to d, then what you will get this equation, that at if you substitute here, then you will get d is equal to, because y is equal to d is equal to h upon w cos hyperbolic w upon 2 h, because x is equal to L by 2 minus y. This is equation 24. If you expand this, it will be d is equal to h upon w 1 plus 1 upon 2 factorial w L square upon 2 h plus 1 upon 4 factorial w L upon 2 h to the power 4. So, w L to the power 4 divided by 2 h to the power 4, and then higher order terms, then bracket is closed minus 1. So, this one will be cancelled, and this one approximately you will get d approximately W L square by your 8 h. This is your what you call, this is a simple task you can do, right. So, approximately d is equal to W L square upon 8 h, and this is equation 26. Therefore, the safety code gives the minimum clearance your height for the line above ground, and if this is added to the sag, the minimum height of the insulation support points can be found. Actually, this sag will be there from the ground, the minimum your safety clearance will be there. In addition to that, you have to add this sag also, right, such that minimum height of the insulation support points can be found. So, whenever you are designing a line, you have to find out the maximum sag what can happen, and that can happen when temperature is very high, particularly in summer season. Next what we will do, suppose this is your same thing A and B at the same support, right. This is parameters of catenary, this is your directrix, this is x, and this is the lowest point O, this is that horizontal tension H, right, and this side is L by 2, this side is L by 2, and here that along this distance, suppose say this is your between L by 2, that your at S is equal to L by 2, this weight is acting in the middle of this portion, right, between O and B, this is the midpoint of the conductor, and your horizontal distance between A and B is L. So, this V is equal to W s, and as S is equal to L by 2, that means this one actually your W L by 2, because S is equal to L by 2, and therefore, this T y, that vertical tension T y will be balanced by this downwards that vertical conductor weight is acting. So, T y will be W s. So, T y is equal to W s, it is written over, and T x horizontal one, say T x is equal to some W c, c is some length, right. So, that is T x is equal to W c some length, and that is equal to h. So, and this one, this is the directrix and this is the horizontal line. So, this angle is theta, this angle is theta, right, and some correction fluid I have put it. So, do not look into this. So, this angle is theta, therefore, this angle is also theta, and this one, this C is h upon W, and this then from here this is the y, this is the sag, this portion is the sag. So, this portion is d. So, we will see later this thing, and total from this directrix, the total is y, and y is equal to c plus d. Now, this is actually figure 3. Just for the purpose of explanation, we have made this diagram. Now, C is the, now from figure 3, it is C is the ordinate of the lowest point of the curve with respect to the directrix, and y is the ordinate of the point of tangency with respect to the directrix. That means, this is the C, this is the lowest point O dash is equal to C, and this from here actually if we take this point from this point to this point, suppose if it is O, this is O dash. So, if I take this is my O double dash. So, O double dash A is equal to D, this is basically nothing but the sag from this height is equal to this height D. Okay. So, thank you very much, we will be back again.